Okay, so now we want to evaluate this integral. And as always, when I say evaluate, I mean compute it if it exists and say it diverges if it doesn't exist. So let's just spend a minute or so, however long it takes, looking at the integrand. So is this an improper integral? Well, we're only integrating over a finite interval. So if it is an improper integral, it's a type 2 improper integral. So let's think about the integrand here. I've got the square root of 1 minus x squared. So for this thing to be defined, I need to have 1 minus x squared. Just for the square root to be defined, I need to have 1 minus x squared being greater than or equal to 0. This is the same as saying 1 is greater than or equal to x squared. And this is the same as saying minus 1 is less than or equal to x is less than or equal to 1. Okay, and we see what happens if x is equal to plus or minus 1, then 1 minus x squared is equal to 0, and so we're integrating over a discontinuity. And 1 is one of our endpoints of the discontinuity. So, or one of the endpoints of the interval we're integrating over. So in other words, the right endpoint, there is a discontinuity, there's an asymptote. This has an asymptote at the right endpoint. And so this is an improper integral, and so we're going to have to take the limit as of integrals from 0 to t. So precisely what we have is the integral from 0 to 1 dx over the square root of 1 minus x squared. This is equal to the limit. This is going to be the limit as t approaches 1, and it's the limit as t approaches 1 in this direction. So it's the limit as t approaches 1 from the negative side. 0 to t dx over the square root of 1 minus x squared. Okay, so now how do we handle this integral? So again, think for a moment about how you might handle this integral. So for any value of t that is strictly less than 1, which is exactly what we're looking at here, this is a perfectly well-defined function. 1 over the square root of 1 minus x squared is continuous from 0 to t if t is less than 1. So we can do all of the normal integration techniques that we want to do. In particular, we can do trig sub. So I can say x is equal to sine of theta, and then dx is going to be cosine theta d theta. And what's going to happen over here in the integral, so this is going to be the limit as t goes to 1 from the negative side. And I'm going to change the bounds. I'll change the bounds on the integral in just a moment. But dx is going to be equal to cosine theta d theta. In the denominator here, I'm going to get 1 minus sine squared theta. Okay, so the bounds on the integral, well, x equals sine of t. So if x is equal to sine of t and x is equal to 0, that means the lower limit here is still going to be equal to 0 because, you know, I need to solve sine of theta equals 0, and that's going to be 0. Now, the upper limit here is going to be a little more challenging. All I can really say is this is going to be arc sine of t. There's really not a lot more that I could put there. Okay, and so now what's going to happen when I do some stuff with the trig sub? This is the limit as t approaches 1 from the negative side. And we're going to look at the integral from 0 to arc sine of t. But what's going to happen here? 1 minus sine squared, that's cosine squared. You take the square root, and for the values of theta that we're interested in, the square root of cosine squared is equal to cosine. So this denominator is cosine. I'll just do this in 2 steps. So we've got cosine theta d theta over cosine theta. So this is the limit as t approaches 1 from the negative side. Cosine theta over cosine theta, that's just 1. So this is the antiderivative of 1. So this is just 1. The antiderivative of 1 with respect to theta is theta, and theta is going from 0 to arc sine of t. And so now this is the limit as t approaches 1 from this side, the negative side. Okay, so let's think of what's happening here. I'm going to put arc sine sorry, yeah, I'm going to put, when I plug in theta is equal to arc sine, I'm going to get arc sine of t, and then when I plug in theta is equal to 0, I just get 0. Okay, so now let's think what's happening here to this limit. Well, think about what the function, think about what arc sine looks like. So arc sine is a continuous function when t goes from -1 to 1. So arc sine is continuous on -1 to 1. So let me record what I'm saying here. Arc sine is continuous on the interval -1 to 1. It's only defined on -1 to 1 because, sorry, I should write it like this. It's only defined on -1 to 1 because sine only goes from -1 to 1. So arc sine is continuous on this interval. And so like pictorially, if this is -1 and this is 0 and this is 1, t is approaching 1 this direction. So arc sine, we're looking at the limit as t approaches 1 from this direction of arc sine of t. So in other words, arc sine is a continuous function. And so this lets us do the following. Arc sine is a continuous function going this way. And so this lets us do the following. This is the this is equal to arc sine of the limit as t approaches 1, t. Now, this limit is clearly 1, so this is equal to arc sine of 1. And remember, for arc sine, we restrict this, when we think about arc sine, we restrict this domain from -pi/2 to pi/2. So arc sine of 1 could be a lot of things, but with our setup, this is equal to pi/2. So this integral is equal to pi/2. And so notice that in order to apply all of our sort of calculus ideas, trig sub, fundamental theorem of calculus, that sort of thing, we have to be dealing with a proper integral. And so the whole point, the whole definition of improper integral lets us look at a sequence of proper integrals on which we can apply all of our calculus tools, and then we compute that in terms of some parameter, in this case t, and then we get this right here, and we take the limit of this as t goes to 1. Okay, and we're going to be seeing more and more of these ideas when we get into series and stuff like that.